All right, everyone. So good morning, good afternoon, or good evening, wherever you're watching these lectures from. So today have our final lecture by Agata in the topic of celestial holography. So wrapping up our first course of our school. So before we start, again, as I said in the first lecture, we are going to send out the certificate as soon as possible. We're going to just check if like the attendance was suitable for immediate certificate, and eventually we're going to send out for the people who are participating. If you don't receive yours in a matter of weeks, please email us and we'll try to solve it out. Okay, that being said, Agata, please.
Okay, so guys, last time on the last lecture, we basically uh, made a fundament for why celestial holography is a holography idea, how this idea is implemented in reality. And today, in our last lecture, we are gonna talk about celestial OPEs, right? Remember the operator product expansions that should appear in any CFT we're studying. We will talk about the algebra, which is, where is, it's, the algebra appearing from these OPs, which is called W1 plus infinity algebra, and it's I think now it's one of the central objects of studying celestial holography. There is a lot of things going on around this algebra, and I think it's nice if we just talked how it appears, where it arises from. And also in the end, I will give a brief bridge between how this celestial holography program is connected to twistor space, which in this bridge will be realized through the W1 plus infinity algebra. This last lecture, it will be less computations, less derivations. It will be mostly intuitive ideas and how we get one idea from the other, how they are connected. And yeah, again, these topics are advanced. Some of the questions I still ask myself when reading the articles and preparing the election. So let's have a little bit of fun in the most modern part of celestial holography. And yeah, let's start. Let's firstly remind ourselves the OPE story, right? So OPE of two fields is when we decompose the product of two fields into some terms in the orders of their singularities. So when two positions inside the fields get close, there appear some singularities in the correlation functions, and the singularities we decompose in their orders our two-field product. And this way we arrive to operator product expansion, shortly OPE. Okay. So yeah, lecture 4. Lecture 4. The finishing ending lecture. Celestial opinions. W1 plus infinity algebra of soft gravitons and its connection to twistors. Okay, so we start with thinking about what going to happen in some scattering process when there are And today we will talk about scattering processes with gravitons. Today, everything that we talk about will be gravitons because, as you can notice from the name of the school, it's the school on gravitational physics, right? Even though most of the things were firstly done for gluons, but gravitons is of most interest for us today. So when we consider some scattering process, and when we have two particles, let's consider two particles, P1 and P2, interacting through a free vertex. What we get is there appear a propagator of these two particles proportional to P1 times P2, right? Because originally we have the propagator of 1 over P1 plus P2 squared. And then since our gluons are massless, the square of their momenta disappears, and we only have their product that is not vanishing, right? So these things disappear. So when we consider some scattering process which involves a free vertex, we get this term, this pole from a propagator. What's going on to happen when we rewrite it in our celestial coordinates? We will get something proportional to 1 over Z12, Z12 bar. Okay, so this thing here, when we consider some scattering process, it will be at most a simple pole at Z1, right? And interesting or important part here that we will consider positive helicity gravitons, and for them we will only need the holomorphic part of the pole. So from now on, we consider and talk about the holomorphic poles of the form 1 over Z1 minus Z2. Okay. So when we consider these singularities, we can write that schematically our celestial OP of two fields, well, it will be two gravitons. Schematically, what we should obtain is something as two operators. Operator 1, then in the point 1, operator 2, at a point 2, here is 1, right? Operator 2 at a point 2. And it should be something singular in 1 over z bar, 1 over z1 minus z2, plus some regular terms. So this is our singular part, which we are mostly interested in conformal field theories, right? This is how our OPE should look like, more or less, right? So we expect to see something like this. And there is a specific constraint that connects the scale and dimensions of two gravitons together. I will not talk about how this constraint arises, but you will be provided with all the links inside my lecture notes. So constraint delta 3 is delta 1 plus delta 2. This constraint should be satisfied for gravitons. Yeah, let me write down that it's not just any constraint, it's just constraint for gravitons. Okay? For gravitons. So when we take this field here, right, it's the same fields as to denote our celestial amplitude here, right? So these are the fields. We consider the operator product expansion of two of them. So when we take some scattering process with gravitons, we need to introduce the primary field connected to gravitons, right? And now to never forget that we are actually talking about gravitons and not just any primary conformal fields, we will denote by function by the following field. We will denote J, big J, plus minus, taken with some scaling dimension here, taken in the in the point z bar. This will mean positive or negative helicity, right? The helicity plus minus 2 graviton. So we will denote this as a graviton field, and it crosses this graviton that propagates somewhere inside the bulk. It crosses the celestial sphere at a point z bar. Okay, so for us, it will be important to consider OPEs of two positive helicity gravitons and positive helicity plus times negative helicity graviton. However, when we consider the two gravitons of negative helicity, they will have only antiholomorphic poles. So it will be something like 1 over z bar 1, 2. We are not interested in that. The analysis also can be performed on the negative helicity gravitons, but we will restrict ourselves to these OPEs. So if we write it down explicitly, we can write two following operator product expansion. First, of a graviton of positive helicity in point z1 bar, and times graviton of positive or negative helicity in the point z2 bar. Okay, and this will give us OPE in the following form if we compute it directly. This will give us OPE with some function E, delta 1, delta 2, together with a third field, which depending on the helicity of the second graviton, it will be either a positive helicity or negative helicity graviton of a weight 1, delta 1 plus delta 2. Z2, Z2 bar. Okay, and these functions here, they can be fixed, and they can be fixed through imposing the Leysen-Soft theorem. We can fix the constant in front of this factor here. Then we impose sub-Leysen, if I'm not wrong, soft theorem. But in any case, there are also articles who fix this constant for us. This constant, not constant, but a function of, right, function of some conformal scaling dimensions, it can be fixed as a beta function. So actually, again, in our celestial story, some combination of gamma functions arise, right? This is just our gravitational constant, right? How it's called, the one that is 32 pg. I don't remember how it's called. Anyway, this is this constant here times beta function beta function of the corresponding weights. So we can, in our celestial CFT, we can fix the graviton OP. That's great. That's very good. But still, what we should do with it? Because this thing here, we obtained, let me say, we got it from imposing the asymptotical symmetries on the form of our opinion. So we obtained it imposing symmetries, asymptotical symmetries on celestial opinion, right? So all the constraints that fixed us this coefficient here, these constraints were the asymptotical symmetry constraints. From the other side, actually, this also completely the same expression can be obtained from purely amplitude part of the question. So I think I will not derive it here because the statement is just that if we consider collinear limit of two particles, so namely collinear limit is when two of the particles are collinear to each other, right? So let's consider this propagator again. 1 over P1 times P2. Let's expand it a little bit in the following form, minus P1 vectors already, 3 vectors P2. And now if we rewrite it, all right, as P1 model, just the scalar product, cosinus theta between their directions, we can write down the following expression. So we see that when they move in the same direction, there is a singularity here in this propagator, and this singularity, of course, corresponds to the same singularity that we were considering here, right? Here, the same singularity, but if we study it in the from the amplitude point of view, we will And here, if we study not already OPE, right? Not just operator product expansion, imposing symmetries, but if we actually write down some endpoint amplitude that has a pole like this. So in momentum space, and then we do a Mellin transform, we will obtain the same expansion, the same OPE expansion for two fields. Okay. So this expansion here, it can be obtained from two analogous ways, and this result is now important for us because after finding this, okay, let's name this paragraph OPE. After finding this OPE, we can finally understand what is W1 plus infinity algebra that people are all talking about. So W1 plus infinity algebra. For this, we will need to take the soft limit of our graviton operator G. So we will define a soft limit, a soft graviton operator H. K as the limit when epsilon goes to 0 of a normal graviton. So the weights, the conformal weights of these gravitons are given by the set of numbers here, where k goes from 0, from 2, 1, 0, and then all the negative integers. So what do we do now is we use the important thing of computing operator of using operator product expansions to find the commutators of fields. So actually, just to find commutator of two fields A and B, we need to take a contour integral over our around one of the points where the commutator is taken of the operator product expansion of two fields. Okay. So some field A in a point W, field B in a point Z, and this way we can compute the commutator of two fields. So now we can, and soft gravitons, we remember, right, that they have different modes. There are leading soft graviton, there's subleading soft graviton, subleading soft graviton. So we can compute the algebra of these soft currents. So the algebra of these soft gravitons, of their currents, as follows. If we just take the commutator of two modes of the soft gravitons. Then we integrate, then we write down this limit instead of just taking two normal gravitons. We take this OPE, we take the limit, and we substitute it all in this integral here. Okay, so when we do all of this, we will get a very monstrous expression. Okay, over 2, and then our indices begin. I will write it down just for you to see how awful and ugly it is. But then we will do a little transformation that will make it all look much more better. -n, -1, there are some factorials, factorials again, over 2 minus m factorial, then 2 minus l m minus n factorial, and then the same thing, but with some pluses inside. I will just copy paste it and then fix the signs. Okay, so here should be pluses everywhere. Here also pluses everywhere, except of the last term. Okay, so this is our commutation relation for two soft gravitons, or two soft currents. Yeah, not forgetting what it is proportional to, right? If it's a commutation relation, it defines some algebra, it should be proportional to one of the currents themselves. Okay, so this looks not very bifactorial, I mean gamma function. I mean, yeah, they are all also integer here, and I'm not even sure if these things here are negative. I think you can just write factorial in this sense, because here k runs from mostly negative things, so this thing will be positive. And yeah, m, yeah, maybe you can use gamma function, but I think here is all right to use. Okay, there's also another question. The first term in the product of the two gravitons can be like a phase term. I'm sorry, I don't know. I don't understand. What is a phase term? But yeah. Maybe if you expand what is a phase term, we can talk about it. Okay, so for me, it seems that the factorials here should be all right, because we have some additional constraints also that we actually have some additional constraint that m lies between 2 minus k over 2, no, k minus 2, and 2 minus k over 2. There is also this constraint. So I would say that it should be just factorialism. But anyway, it's not the point. It's just it can be just some coefficient depending on the indices, on the orders of the soft gravities. But yeah. So now, if we do the following transformation, if we write down, we redefine our currents, to get this commutational relation in a simpler form. If we do such a substitution, 1 over, sorry, kappa p minus m minus 1 factorial p plus n minus 1 factorial, and our soft graviton 2p plus 4. Okay, if we do such substitution, here we define it, okay? This commutational relation will take much simpler form. And this much simpler form will be something that defines our W1 plus infinity algebra. And this is the expression for the commutator that we arrived to. Omega, sorry, W, something, some letter between omega and W. P plus Q minus 2. Okay, and this is the commutation relation that defines the W1 plus infinity algebra. This algebra has been known since 1989. It arose in CFT, in two-dimensional CFT several times, and it also is known as algebra that preserves the area on the plane. So this is something already known to humanity. And this is exciting because now we can find connections with different areas of mathematics, of physics, and to learn maybe something more. Maybe someone already studied this algebra, and we can learn some more properties about our gravitons, about our soft theorems, or just the celestial CFT itself. And yeah, this is an important result. Now people study a lot this algebra, how it generated, and now I think the time has come to tell how it can be connected to twistors and string theory that people do. So the later will be based on how I understood the paper. Let me. Where is it? I can't find. Anyway, the paper article. Celestial W1 plus infinity symmetries from twistor space by Team Adamo and some other people, Mason and Sharma. So I will not go into strict rigorous details in this paper. I will just try to give a brief idea of how it's expected to find this connection with twistor space and why they actually found it. So let's briefly mention what is a twister. Actually, I will mention how the twistors are connected to Minkowski spacetime, and then the later study of twistors is up to you guys. So let's start with so the paragraph will be connection. What is the year of the paper? Let me just find an archive because it's just somewhere here hidden. Is it this? No, this is not it. Just a second, I will give you an archive. Yeah, okay. So two 2110 period 06066. This should work. Yeah, great. Thank you. How okay. So yeah, let's first mention the connection of Minkowski spacetime and twistors. So to construct a twistor space in general, we connection of one with infinity with steps. So we start from Minkowski space, where vectors have the form x0, x1, x2, x3. And they live in a Minkowski space, which is defined by metric minus plus dx0 squared minus dx1 squared minus dx2 squared minus dx3 squared. And then we complexify each of the components. So x0, x1, we complexify them. We complexify x mil, which means that x0, x1, x2, x3, they are complex numbers now, but metric is still preserved. Plus the metric. Okay. Now we can transform out of this complex vector, we can transform a matrix. So we transform, we construct 2 times 2 matrix as follows, with 2 indices because they are the undotted index, the index and the dotted index. It's the spinor notation, but again, they are just different. They will be treated differently and raised and lowered by different things. Okay, so they are of different genre. It's Levi-Civita, two-dimensional Levi-Civita times again two-dimensional Levi-Civita. This is how we define the lowering and the here raising rule. Okay, so we can go from the matrix with upper indices to metric with down indices like this. And it's connected to our 4 vector, which is now complexified vector as follows: x3, then minus x1 plus I x2, minus x1 plus I x2, and x0 plus x3. Okay. So these indices here, they're all of them are going around 0 and 1. So both dotted and undotted indices, they can take values 1 or 0, or 1 or 2, whatever you like the most, the numbers. So, and the Levi-Civita symbols here are defined as follows, but again, it's depends on your definition. You can define them with some different signs. It's just important for you to be consistent inside your work. Also the dotted Levi-Civita. And these Levi-Civitas act as matrices that lowers our indices and raises. So, for example, if we have some object with the upper index, we should apply the Levi-Civita on the right. And if we have some object with a lower index, to get an upper index, we need to apply the Levi-Civita on the left. But it will be not very important for us. I'm just trying to explain the notation that I wrote. I will not write down anymore notations. It's all very heavy kind of tools that is not really in the scope of our lectures. So we constructed these matrices, and now we have these dotted and undotted indices. And now we construct our twistor space. It's a mathematical construction. I will only right now not actually define it, but write the connection of a twistor space, which has twistor space has 4 coordinates z a, and these coordinates will be given as a set of mu with a dotted upper index, where alpha can have values 0 dot and 1 dot, okay, and the variables lambda with undotted index. And these variables are connected in a non-trivial way with the Minkowski space coordinates. So, and this is the following connection. So we have constructed our matrix out of just complexified Minkowski spacetime, and these coordinates of the twistor space here, they are connected with the Minkowski space in the following manner. So this is all the coordinates are complex, and I would say that this is enough of twistors for today, because again, it's a very rich topic, and I'm not a specialist in it. But what another thing that I should say, that this is all was in Minkowski, right, with the following metric, but our spacetime, even though being asymptotically flat, it is not Minkowski, right? It's curved, so the metric has different has a different form, and so when the spacetime is not flat anymore, our twistor construction will be not that straightforward. There will be, as far as I understand, there will be some deformations of it. We need to introduce some new structures corresponding to the gravitons that deform our twistor space. And I will not discuss it, but just keep it in mind. So this is how twistors arise. This is what they mean, flat Minkowski space. And now to see the intuition behind the connection of W1 plus infinity algebra with twistors, let's take a little step back and just how it is connected with W1 plus infinity. So I see some question. I don't find what is the role of this lambda in the pair defined in the twister? I mean, it's a coordinate on the twister space. There is like 4 coordinates. I will not talk about the structure of how this space is actually mathematically properly defined, but it's just 4 coordinates. They are all complex on a space, and these coordinates are connected with Minkowski space through this expression. You can just treat it right now as a coordinate. If you will want to really understand what's going on, I refer you to, for example, Tim Adamo's lectures on twisters. Okay, and seems like it's very good lectures. And yeah, right now we just want to see the, so to say, intuitive approach to all these things, right? Because we already spend almost an hour, and right, there will be not enough time, and also, yeah. So here is our twistor expert. Yeah, so Raphael writes that each one of these coordinates is a spinor of opposite chiralities. They are related by the coordinates in space-time written in terms of, yeah. Thank you, Raphael. Yeah, you can discuss. For me, so now, yeah, let's do the important step here. Is how it's connected with W1 plus infinity. So let us consider. Let's consider um, mu alpha dot to be mu alpha dot to be complex coordinates on a plane. So coordinates on the complex plane. Coordinates on the complex plane. And let's define the Poisson bracket as follows of 2 functions on this plane. Let's define their Poisson brackets as df over d mu 0, dg over d mu 1 minus df over d mu 1, dg over d mu 0. And equipped with this Poisson structure, we will also write down the following polynomials. We will consider the polynomials W, right? When the W arrives, it means we're close to the W1 plus infinity symmetry. So W is the following polynomial in these 2 complex variables, mu 0 and mu 1 minus 1, and mu 1. Minus n minus 1. Okay, and there is also constraint on m and p. So if we take these two polynomials, and we act with a Poisson bracket on two of them, we will get a magic which will reproduces the W1 to infinity algebra. So the indices here, W m plus n equals q minus 2. Okay. And yeah, this is the same algebra that we just derived from the soft graviton cards, given just by some mathematical construction on a complex plane. But again, this is just some mathematical construction. What are these things here? It's not motivated. Why should we use them, even though they give a good commutator for us? In reality, if we go to twistor space from these coordinates, we somehow reduce the twistor space to these two coordinates. It's, if I'm not wrong, it's like this thing here describes like a patch of a twistor space. So when we go to the twistor coordinates, then we need to introduce some action on this twistor space, right? So we go to twistor space. Then we introduce some action. In this article that I cited, we introduce twistor sigma model action, introduce action, and then we define the corresponding Hamiltonians from this action that correspond to that represent soft gravitons. In this theory, then we introduce Hamiltonians. We will notice the notation for these Hamiltonians will be the small letter g. They defining corresponding related to, say, representing is the proper word, representing soft gravitons. So again, we will not perform all of this construction in our lecture, right? It's this construction from the Adamus article. And so if we do all these things here, so we go to twistor space, introduce some action, and introduce these soft gravitons inside our theory, our constructed theory, we will obtain the W1 plus infinity commutation relations defined by this Poisson bracket. So if we take this commutation relation of two Hamiltonians that correspond to the soft gravitons of the theory, we will, the bracket is the same, okay? Just a little, the coordinates will be rewritten in some, in the twistor space. We will obtain again our W1 plus infinity algebra. So this algebra here is not just some random consequence um, of our analysis of some symptotic symmetries, right? Of the form of graviton OP, so graviton OP. We can actually obtain it from setting some string theory model, some sigma model on a twistor space. And this motivates us to use actually the twistor space for finding such an algebra of fields. So yeah, I hope it was exciting because I think it's always interesting when high level topics in physics are somehow intertwined with each other and connected. And in this in the last section, I know I'm aware of the lack of computations, calculations, and derivations, so it's equipped with a lot of references. My lecture notes will be also I will send them. I will send them shortly after this lecture ends. That's what I wanted to say for today before officially finishing the lecture. I want to, how do I share? I want to share this funny picture here. So remember that reality is an illusion and the universe is a hologram. And bye with this. I hope you found our little journey interesting and exciting. Maybe you got some inspirations for your research, for your studies, or just for theoretical physics. That was very important for me, that maybe you learned something new, something nice, something interesting for you. And bye-bye, everyone. Thank you for your attention.